All right, this is the history of robotics part 2. What is a robot? What you will learn is the difference between industrial robots and other robots, the 4Ds of robotics, and where and why we use robots in the modern world today. What is a robot? The term robot is less than 100 years old. Um, if you remember back from part 1, the Czech writer Karl Kapek came up or created the word robot from the Czech word robota, and he was really trying to find a word that described the drudgery of a machine that was tasked with doing slave-like labor. Um, the liberal use of the term since that creation, less than 100 years ago, was to describe a fictional machine that did different tasks that were human-like, that emulated human actions. So different industrial movers, toys, some information gathering devices and programs. All of these have those types of pieces associated with the word robot today. The Oxford English Dictionary has it as a machine capable of carrying out a complex series of actions, especially programmable by a computer. But then there's other pieces that have to do with computer sensing type of program, or in the case of South Africa, it's a South African set of automatic traffic lights. So it's kind of all over the place with regards to the definition. So really, what is a robot? Well, according to the Robotics Industries Association in 2012, they came up with a piece that had to do specifically with an automatically controlled, reprogrammable, multi-purpose manipulator programmable in three of axes, three or more axes, which may be either fixed in place or mobile for use in industrial automation. So that's for basically an industrial robot. We don't work with those that much in class. So really, what is a robot? And this is going to be our classroom definition in general terms. It's a machine equipped with various data gathering devices. So a way of engaging the outside world, finding different pieces, processing that data, and then having the ability, tools for operational flexibility and interaction with the system's environment. So are we outside? Are we inside? Are we on pavement? Are we on grass? Are we climbing up a wall? Are we interacting with a door? Are we picking up something? All of those pieces with the environment, and then carrying out actions. And here's the piece: it could be either programmed or have direct control. Either works for us. One of the key features with regards to defining the modern robot and what we're going to utilize has to do with that operational flexibility. By this we mean you can change what the system does, how it does it, why it does it, usually by changing the programming, but it can also be done with changing parts. This capacity is what separates a robot from other machines in both the home and in industry. Robots are about options. So we're looking for the ability to do one thing and then do another thing with the same piece of equipment or with small tweaks. So a robotic arm may pick up and place parts one day on an assembly line, then we can move it around, change it a little bit, augment it if you will, then it could be spray painting another day. And then maybe later on we realize that we could have it detect leaks in a device, such as a tire or a pressure vessel, and maybe only a few programs need to be rewritten or a couple different tooling has to be created. So really the key to a robot versus other equipment has to do with that flexibility. This is the difference between a robot and other specialized equipment. So we need to understand that that operational flexibility is a big piece of it. By our definition, one of the first robots created would come from Hans Bullmann. He created a robot, and most people you would remember an automaton, But in this case, it was able to interact with people or the environment, manipulate and move things, carry out tasks. So, if you're looking for that, there aren't any real original Hans Bullmann manipulate devices left. They didn't survive, but they do meet that modern definition. And he lived over 150 years ago, so it was quite remarkable what he did. So one piece that we should know, the term and definition of robot is a fluid and changing. It undergoes changes from time to time. It has in the last 20 years. And if you go into the field of robotics, what's really cool is you have the opportunity and a good chance of potentially making and changing some of those future refinements that I'll be teaching about maybe 10, 15, 20 years from now. So why use a robot? We're here on Earth. We've been successful as a species, and the Earth keeps on turning, and nothing really, do we really need this technology? Just like any other technology. So why do we use robots? This is a good question. Many of you probably have a million answers to that, or at least a few hundred responses on why we would use a robot. Most of those responses, however, can be classified, and that's the 4Ds. The 4Ds have to deal with what the robot is going to be tasked to accomplish or do. And that may be dull, all right, work, which describes tasks that are repetitive in nature and often require little or no thought whatsoever. So if it just requires turning something every few seconds, for every minute of every day, we can assign a robot to do that, such as on an assembly line, which is you can see below the dull, which is really slow and boring. All right, not that much fun. So dull is going to be a situation where we want to just take somebody out of there. It's going to be mind-numbing and not worth the training. There's not much training to it, and it's important that we don't mess it up at the same time. The next would be dirty. We have our little Wall-E buddy down there from Disney's Wall-E. Dirty has to do with tasks that involve the process of dust, grease, grime, sludge, substances that people would rather pretty much avoid. Garbage. Such tasks may pose a mild health risk, so we don't want to have allergic reactions or anything along those lines. But for the most part, these jobs are going to basically the job would leave the people covered with something at the end of the day, whether that's some type of grease or dirt, something along those lines. We just send the robot to clean it up, take care of it, and we as a human race avoid that situation. Difficult. The construction of various machines, it's a production process. It might require multiple tools, rapidly used, very hard for a human to be able to meet the response time, those types of pieces. Or it could be something where we need to be able to rotate 200 degrees, and for a human to rotate 200 degrees, it's very difficult on the human body. For instance, a human elbow only has about 90 degrees to maybe 100 degrees of motion, and we can make robots that have 120 all the way up to the 270. In some cases, you might need to rotate a full 360 degrees, and we can do that with no real difficulty whatsoever. The fourth and final D is obviously that dangerous. This environment can be excessive, hot, contain toxic fumes, radiation, working with unguarded machinery, or conditions that could kill somebody or have harmed somebody already, and it's more easily or readily available to send in a robot to complete the task. The robot here is going to be retrieving a wounded soldier from the battlefield. Instead of sending in more human beings, we can just send in a robot to capture and recover our wounded soldier. So going beyond the 4Ds, what we have here is, and this is you know, the dull, dirty, dangerous type of lifestyles and difficult lifestyles or tasks that we're going to have robots undertake really come down to precision. And that's the performance of tasks accurately and exactly within given quality guidelines. So what do we want to have taken place? Well, it's also, so it's important that we're able to diffuse the BOM, organize the parts the same way every time, paint the same color with the same, pieces, and that's great. So really it comes down to precision. A robot lends consistency and repeatability that is difficult for their human counterparts to match. Consistency is what we're talking about there. The ability to produce the same results and or quality each and every single time. So we have Baxter here on the screen, and you can zoom in and see what he's kind of made up and how he works. With the degrees of motion and freedom, the payload, he's able to lift 5 pounds. Pick and place operations, from 8 to 12 pick and place operations per minute. He's got cameras, he's interchangeable, he can do different things. Those pieces, as a robot, we can spend time, with a robot, you don't have to worry beyond just getting the programming right, making sure the mechanical and electrical components are in place. Once that stuff's taken care of, and with a program we can just save it and come back to it later. If we want Baxter here to do a task on Monday and a different task on Tuesday and Thursday and Friday, and then it's Monday again, we don't have to retrain him or remind him. He just calls up the new Monday protocol and he does the Monday protocol. Or if we change it every other Monday or every July 3rd we do this, Baxter can do something and it's not a matter of remembering. So as long as his electrical and mechanical components are valid and working, and he's receiving the signals that he needs to receive from his data processors, he can perform the same task no matter what for 1 hour or 48 hours, Monday morning, Friday afternoon, whether the company's hiring or laying off workers. It can consistently work, and this is going to reduce costs. It's a cost-saving measure. So cost saving is a factor that has helped to drive the integration of robotics into the industry. We've discussed this in the past. And another why for the industrial robot is, in industry, workers are generally paid, by the hour or by the piece that they create, and then they obviously get retirement and insurance, those fringe benefits, Social Security, life insurance, all those things. Robots don't require that. So a robot, once you get past the initial cost and then the upkeep and maintenance, and then depending on how complex the robot is and what you're doing, a robot can pay for itself in 2 years and work to the point where you're paying for it to be in place at roughly the cost of 42 cents per hour. So it's very easy to understand why robots are going to go into other places beyond the 4Ds, because, well, the 4Ds, we want to avoid those just as human beings. Robots have the capability of taking over certain higher level pieces. So now, going even further beyond the Ds, there's new robotic systems that have to do with telepresence. The telepresence basically allows you to be in one location and be engaged and interact as almost an unique individual in another location. The Beam Plus and Beam, you're able to maneuver hallways, move along, go in elevators, walk and talk and have conversations, and you're sitting in your living room, you're sitting in your family room, you're sitting at your kitchen table having coffee while you go to meetings and have conversation. And that conversation could be taking place in Germany while you're sitting in New York City, or you're in Australia on a beach and having a conversation with somebody in a high rise in Tokyo. So the telepresence capability is something that's definitely on the rise. And then, of course, the research capability. Research is one area that is heavily invested in the robotic systems. We use robotic platforms to test new design ideas, technologies, programming methods, or even algorithms. And I know that most people are going to think math algorithms, and that's correct, but algorithms are really just a systematic procedure for solving a problem or accomplishing a task. So we're able to test these out before we have to put them into mainstream service. Research robots go places and do things that are just too dangerous or difficult for us to travel as humans. So why risk that exposure to the human, to the human traveling to 2 miles below the surface? We really can't survive there and do as much information and data gathering as an ROV there, as seen. And we can also start to test and look at how kinematics and walking systems can lead to other growth in other areas, such as going into robotic augmentations. I don't think there needs to be much words with this. This is pretty awesome where we are headed with robotic augmentations. Robotic augmentations, if you remember back from part 1, we talked about Per Ambrose, who introduced the concept of combining flesh and mechanical parts in 1564, and talking about how we could have organic and mechanical components working together. And then if you remember in 1998, Campbell Aird's surgery where they fitted him with a bionic arm that utilized a biosensor. And just so that we understand what a biosensor is, so that we can understand what the augmentation is, a biosensor is a device that picks up the electrical activity associated with a movement through wires that are incorporated into the surface of the human being's flesh or skin. And then we're able to use electrodes to manipulate the currents that are where the brain sends a signal, and we're able to capture that current and interpret that as a motion or a movement. So the biosensor picks up that electrical activity, and then we get an action off of that electric activity because of the actuators from the robot. This has been done in prosthetic legs. There are segmented feet, special joints. We're using Bluetooth actually now to communicate between pairs of prosthetic legs. So if a person had lost both of their legs in some unfortunate situation, we can use Bluetooth to coordinate their motions so that they don't have, they can walk more naturally or run more naturally and not have any issues. And then of course what we have on the most extreme version of this is an exoskeleton type of system, which allows people who can't move pretty much at all to start walking again. I think this is one of the most exciting parts of robotic systems, is an exoskeleton that straps around the user's body to enhance strength, endurance, and in some cases mobility. There's a company called Rewalk that is really working on this. The system consists of robotic exoskeletons to fit around the user, and then sometimes you have to use the specialized crutches to help the wearer keep his or her balance at times. But this system can, at this point in time, keep a wearer mobile or in a much more humane or intended position in terms of walking for up to 2 hours. And as we develop these systems, they're going to get much more involved. And in fact, the military is working on these, where now we create this kind of system where this exoskeleton system can allow a soldier to carry many times his own weight, obviously her weight if necessary, and moving supplies that would be very valuable to their success and or survival into locations that were otherwise difficult for other transportation systems to take place. So in conclusion, what you should have learned is the difference between industrial robots and other robots, the 4 Ds of robotics, and where and why we use robots in the modern world. Whether it's the 4 Ds of robotics, simple human desire or performance requirements, typically a robot has worked its way into many aspects of the modern world that we live in now. While the specifics of why we use a robot is usually linked to some application, the broad answers remain the same. The robot is either performing a task we want to do, a task we wanted to do, a task we as humans do not want to do at all, a task that is dangerous for us to do, or a task that requires precision and or a force that we cannot as humans create on our own. It is because of this the robot is really an advanced piece of technology that's earned its place in our modern world and will continue to be a part of our world into the very, very distant future.